We got to retain them. How is it done right now? Traditionally, it's done with stainless steels, Inconels, titaniums. So we're using a metal to retain those magnets. We're putting a sleeve around the outside of the magnets overall. There are pros and cons to that. Some of the pros are that you've got non-magnetic material. You need to have that non-magnetic material. And the coefficient of thermal expansion is going to be a little bit more in line with the magnet itself. So you can easily design your expansions as you heat up and cool down your rotor overall, and you know where you're going to be performing. But what else can we do? I mean, what else is out there? Because one of the cons is that these things, they have their own weight. Metal is dense, so metal itself has a lot of self-induced stress. So when that sleeve is rotating at a very high RPM, it's using a lot of its own strength just to keep itself, in one piece to not break apart just because of its density. So that's a con that we need to look into. The electrically conductive portion of being a metal, they are electrically conductive, and that's sometimes good and sometimes bad. Sometimes it's good because you want to take the heat out of the rotor through the sleeve, but also bad because you have joule losses. We're making the system less efficient overall. So what are we doing overall? We are working to design, manufacture, and validate through our tech center newer sleeving technologies, and that would be carbon fiber sleeving technologies that we'll get into some more detail on here. So why carbon fiber overall? We definitely want to think about carbon fiber and look and see how we can use this in your applications. One of the biggest things about carbon fiber is that it is a lower density. It's a lower weight type of product, and that's why we see it being used so much in, let's just say, aviation and aircraft now. Some of those planes that are up there are some of the most carbon fiber structurally based platforms that we've seen throughout our entire lifetime. So that technology is now making its way into the components, into the subcomponents. And the same thing's happening with our rotating electrical machinery. We see that carbon fiber is being used as a sleeving option to keep these magnets in place. So they're good because they reduce the impact of the overall mass of the rotor, hence its inertia. So now I don't have a really heavy sleeve now trying to kind of rip itself apart. The carbon fiber can do its job without having a lot of its to just support itself. It can do its job. It can hold those magnets in place with its strength. That reduced rotor mass can also allow you to use smaller bearings. So maybe you don't have as heavy of a rotor creating so much inertia, and maybe you can design the whole system to be a little bit smaller from that standpoint, or use less heavy duty other components with your system. Then we have lowered self-induced stresses at RPM. Again, the sleeve not being dense or as dense as metals means it doesn't have to hold itself on. It can do its job and hold those magnets in place. Carbon fiber is very strong. We all know that carbon fiber is very strong per its unit mass. So 0.2% yield strength at Inconel, they're typically around 1100 MPa. Stainless steels maybe in the 300 to 400 range. But if we look at carbon fiber, we know that we can get carbon fiber that's 2,000 megapascal, maybe 3,000. We know we can get really strong carbon fibers, and then obviously we need to then design in a resin. What resin material are we going to use? What's my tensions? How am I going to assemble it? So we're not going to get all the way to those strengths, but we know we can get well above the traditional Inconel 1100 MPa range. So we can get stuff that's a lot stronger, a lot less powered, a lot less dense to then increase the power density of your system overall.